For what? January the 7th? Alright, let's do this. Another easy one. Count prefix and suffix pairs. Define a Boolean function is prefix and suffix that takes two strings, 1 and 2. Returns true if string 1 is both a prefix and suffix of string 2, and a false otherwise. For example, this ABA and AB is true. This is false. Return an integer denoting the number of index pairs such that this and this is true. So we just go through everything and then do the comparison. I wonder if they can figure out some, random algorithm to do this compared to just brute force this thing. Yeah, we're just gonna brute force this thing. Don't want to think. What are we returning? The number of pairs, right? Is pref suff is W1 is a prefix suffix of W2, yeah. Is larger than, right? Yeah, so if it's this, turn 0. Otherwise, I feel like these two can put it together. I think I need n minus I minus 1. Right? Because I start from here and then I start with 0, right? So and suffix. All right, let's try it. Oh wow. Oh wow. Okay. My bad. I did not realize this one can happen. Oh wait, hold on. That's not right. Ah. Yeah, I see. Alright, so basically it should be n minus 1. This should be m. Alright, that's an oversight. Yep. Yeah, this is nothing to... Oh, I forgot to write. No. Let's say k squared times m times n. Dual try. We're doing a dual try. So we have a prefix and suffix. So we build a prefix try and a suffix try. And then for each word, we just check through them. No. Yeah, we go from right to left, and then we build a prefix try. So for each word, we'll try the try first, and then we'll build it into it. And then we do another one from front to left to right. No, we do the same thing, and then we flow. I see if that's what we want. Reverse. Yeah, I think reverse is actually a better idea. Just want to see the implementation. Insert a word into try. Oh, we use node links 26. Exists, we check. Insert a new node. starts with yeah. We get prefix and suffix. For each word, we create a prefix trie, we create a suffix trie. Insert prefix trie. Reverse the word, and then suffix trie. That's not what I thought. I thought it's to go from right to left. Because as we go from right to left, before we hit a word, everything bigger than it has already been considered. Right, so right to left, we create a suffix trie and a prefix trie. I think it's the same. I don't like this way. I don't think it's right. Because you already add for each I, you add it and then you iterate through all the previous words. Then a trie, it may have some things in the front. I don't know. This doesn't seem right to me. I don't think I'll iterate this way. I think I will iterate from right to left, which I think is the more correct way to go. All right, I want to see if I can prove it, right? So basically, this is a problem where we have the number of arrays, right? This is what we want. I want to find out the number of arrays. And what we have is we have k numbers, we have n numbers, right? N numbers. We have n numbers, and each one, let's say, can only do this, right? And now we have a k indices. So, we have k indices. What we want to find out is basically what we're saying is there are always only k minus 1 entities. No, k entities. There are only always k entities. there are always n minus k entities. Right? So when k is 0, on k is 0, we have n minus k entities. So everybody is just by itself. Like it doesn't matter, right? When k is equal to 2, then we have 5 minus 0 is 3 entities. Because I point in there, that's 3 entities. Okay, so now we just need to prove it, right? So what we know is each arrow, right, will create its entity. So if I have 2, right, so the maximum you can create is by itself, and each one will occupy 2, right? Each one will occupy 2. So if I have k, then the maximum will have 2k entities, right? And then we have something left. We'll form the third entity. Now, if n is even, then the max without overlap is n divided by 2, right? This is the max entity, is n divided by 2, which means k is equal to n divided by 2, and you will get n minus k entities, right? That's good. So if k is smaller, n divided by 2, then we have k entities, right? And then we have n minus 2k entities left. So we put together, this will give you n minus k entities. That's good. If k is larger than n divided by 2, right? So we have too much k. Now we have too much k. So actually, it's not. This is just even distributed. So we can have some k combined together, right? Some k can combine together. So whenever we have 2 combined together, then they will occupy. So initially 1 will point to 2. If we go 2 together, then we'll actually get 3. If we get 3 together, then we'll actually go over 4. So just the number clumped together, they will occupy 1 more, right? So I can say 2 if separate, we get 4. 2 if put them together, we get 3, right? We occupy 3 values. 3 will be and then become 1 entity. So entity-wise, we have 3 entities. Now we basically lose 1, right? So we minus 2. So we always have only one extra. So if we remove 1, merge together. We're losing 1 entity, right? Because they're being together. But when I lose this entity, we get 1 back. We get an extra entity back. So we lose 1, we get an extra 1. We lose 1, so in the end, we are not losing any entities. right? So we lose an entity, but we gain it back. Yes, that's the thing. You lose an entity, you gain. So initially, right, you have pointer. We require this. This is the initial entity, right? And then this is another entity. So if we move this one here, so this become entity, and this remains because this is an entity. This means no matter how you move, the number of entities doesn't change. So you have n minus k entities. So now you have n minus k entities. Now you know, so one of them is m, the other is going to be n minus 1 times n minus k. Well, minus 1 because you have one extra out. So yeah, we do that. And then you need to see how you can put those k, right? So you do a combination. Yep, that's it. So I need to write it down. We need to find out how many independent entities a good array has, right? Now for each index marked by k, it must have the same value as index minus 1. Thus, we say these two elements form an independent entity. Now, if another index marked by k is attached, is placed immediately after the previous index, then then our entity has 3 elements. Okay. Now we can consider any combination, any placement, right? Placement of indices, right? Now, if we move one index, right, to another place, another position, and create a new entity, we can see that no matter how we move the indices around, the total number of entities remain the same, which is n minus k. This is because if we move one index to another location, its original location does not lose an entity, right? It does not lose an entity. And the new location does not gain an entity. And sequentially, the first entity has m different choices. The remaining entities all have n-1 choices. Then the k indices can be placed in any combination in the n-1 positions. The index cannot be at position 0. We have the solution. With these two pieces of information, we have the solution. Combination, right? And non-possibility. Times pow. And then return possibilities times combinations. And then mod. Oh, I think it's the same, right? Yeah. All right, okay, move on. Oh, design a task manager. All right, some other time. That will be it for today. I'll see you guys tomorrow. Adios.